In this work, we present an algorithm for orienting novel 3D objects by learning to predict the relative orientation differences in a large dataset of 3D object meshes. In automation, it is important to orient parts for many applications including inspection, assembly, packing, and manufacturing. Consider a robot in a warehouse picking objects out of a heap, and it needs to reorient them to pack them in a specific configuration. When objects have a 3D geometric model, the robot can use the model to estimate the physical pose and plan a specific reorienting motion. However, objects don't always come with 3D models, and it can be time-consuming to create them. We thus explore reliably and precisely reorienting objects without prior knowledge of object geometry. We propose a system in which a robot takes an image of the object currently in its gripper, compares it to an image of the object in its goal orientation, and then reorients the object to the desired configuration. We also want to learn how to do this without needing manually labeled data. Self-supervised learning removes the need for manual labels by producing labels as part of the data generation process. We also want to leverage simulation to simplify and speed up the data generation process, which can be time-consuming. Then, we can transfer results from simulation to reality. We propose an algorithm that reorients previously unseen objects with unknown geometry given a depth image of the desired object orientation. We leverage simulation and self-supervision to train a deep neural network to estimate a 3D rotation between two depth images. Prior works that can be used to reorient objects use statistical methods for pose estimation. These works take in RGB or RGBD images and estimate the 6DoF pose of an object. These methods evaluate on datasets such as LineMod, which contain known geometry of each object. In contrast to these works, we propose a method that does not require prior knowledge of object geometry and can generalize to objects outside of those seen during training. Many prior works use unit quaternions to represent their rotation, and so do we. But very recent work has developed novel representations of SO3 that may be better for training neural networks. Prior works can estimate poses for objects unseen during training. However, some methods require 3D mesh or multiple views of the same object to reconstruct a 3D template, while others require that the unseen objects must match the same category or shape template as objects used for training. Prior works in point cloud registration estimate the rotation and translation between a pair of point clouds, whereas we estimate the rotation between a pair of depth images. The most similar work is KeyPointNet, which uses 3D keypoints to estimate the orientation difference between unseen objects of unknown geometries given RGB images in two poses and knowledge of the object category. Another work estimates the relative pose between two cameras given RGB images from each. In this paper, we make the following contributions. A self-supervised objective to train a convolutional neural network to estimate the rotation difference of a 3D object in two different orientations using two depth images. A controller that uses the CNN to reorient objects into a desired orientation without a reference 3D model or a reference orientation. Additionally, we have simulation experiments suggesting that the controller can reliably orient 22 novel objects by up to 30 degrees over 100 trials per object. We also show sim-to-real transfer of the proposed network, and physical experiments suggesting that the proposed controller can orient 5 novel objects by up to 30 degrees over 10 trials per object. To orient objects, we first train a CNN to estimate the rotation difference of a 3D object from images. Then, we define a controller to orient an object to a given pose. Next, we set up a pipeline for applying the network trained in simulation to orient physical objects. To train the CNN to estimate the rotation difference, we first need a dataset. We generate a dataset of images in simulation using the Python library PyRender. However, these smooth depth images are perfect renderings, so we do some image processing. We make the network robust to occlusions by generating random cuts on the image. We also zero out random pixels to further improve robustness. Now that we can generate images, we create the dataset. Each data point in the dataset includes two depth images as inputs into the network, IS for the start image and IG for the goal image. We sample these orientations uniformly from SO3 and filter so that the start and goal images are between 0 to 30 degrees apart. We record the ground truth label of the rotational difference as a unit quaternion, which has real component positive. We use 872 objects from prior work in grasping. We select 80% of the object set as training objects and 20% as test objects. We also select 100 non-symmetric objects from the full dataset. This dataset is useful for evaluating the angle difference between the current pose and the desired pose, because the objects are invariant to symmetry. We use the dataset to train a CNN. The CNN takes in two depth images which go through a resonant backend and get embedded onto a feature vector of size 1024. These two vectors are concatenated and go through fully connected layers with leaky ReLU and dropout to produce a unit quaternion estimation of the rotational difference between the two depth images. We first started training the network with a mean loss function. This function penalizes the angle difference between the predicted quaternion and the ground truth quaternion. However, for objects with rotational symmetry, there can be multiple quaternions that result in the same effective final pose. To remedy this, we use the shape match loss function from prior work that does not penalize correct rotations on symmetric objects. This function compares the point clouds of the object after rotating according to the ground truth quaternion and the predicted quaternion. During training, we noticed difficulties due to the quaternion double coverage property. To remedy this, we define a hybrid loss function. We train with the mean loss in the first epoch and the shape match loss in the following epochs. After training the network, we evaluate the performance of the network on individual data points in the test set. In this example, the object starts in the orientation given by the start image IS, and we want it to reach the orientation of goal image IG, that is 26 degrees away. The network proposes a rotation that can reduce the error between the final image and the goal image to below 0.1 degrees. For this start and goal image pair, for this hammer object with a tilted handle, the proposed prediction will actually increase the error from 23 degrees to 25 degrees. We evaluate the results of the network trained on the non-symmetric dataset. The x-axis represents the difference between the start image and the goal image of the data points in the test set. The y-axis represents the angle difference error of the estimated rotation. We compare the performance of the network trained on the mean loss and the hybrid loss. We observe that we get an average loss of 6.1 degrees when trained on the mean loss and 5.8 degrees when trained on the hybrid loss, and 22 degrees according to an iterative closest point baseline. Next, we show results on the full dataset. The x-axis shows the rotation difference between the start image and the goal image of the data points in the test dataset. The y-axis shows the shape match loss that is robust to symmetries in the object. However, this provides no conceptual intuition like the mean loss. We observe that the hybrid loss performs significantly better than the mean loss. This makes intuitive sense because the hybrid loss does not penalize rotations that are different from the ground truth quaternion, but result in an orientation that looks similar to the goal image. We now have a network that can effectively estimate the rotation difference, but we do not want to perform a one-step rotation. We observe that on average, the error of the prediction is less than the difference between the start image and the goal image. This means that if we make incremental changes to the object, we expect the object to progressively reach the desired orientation. We define a controller that can orient novel objects using the CNN. First, we receive the current orientation of the gripper. Next, we capture the image of the object in the current orientation. Using this image and the goal image, we have the network output Q hat, an estimate of the rotation difference between the two images. Next, we check the angle of the rotational difference estimation. If the network predicts that the rotation between the two images is less than a threshold delta, the controller stops because it thinks that the current orientation is close to the goal orientation. Otherwise, the controller rotates the object according to the estimate. We do not perform the full orientation. Instead, we orient the grippers along Q hat to the spherical linear interpolation of the current orientation and the predicted final orientation. We apply the controller to test objects in our simulated environment. For one trial, we generate start and goal orientations that are sampled uniformly from SO3 and are 30 degrees apart. Then, We run the controller and orient the objects incrementally over a max of 50 time steps. For the vast majority of trials, the angle error decreases from the initial 30 degrees, and for this example, it decreases to 1 degree. We show the results of all trials in the simulation experiments. We take 22 non-symmetric objects from the test dataset and have 100 trials for each object for a total of 2,200 trials. The x-axis shows the final angle error from the goal image when the controller terminates. The y-axis shows the frequency of each histogram bin. We plot all the trials and see that the majority of final angle errors are below 5 degrees. We observe a median angle error of 1.5 degrees across the 2,200 trials. This is a significant decrease from the starting angle error of 30 degrees. These results suggest that the controller can effectively orient objects from 30 degrees in simulation. We perform experiments on a physical robot with a fixed overhead depth camera and an RGB camera. We use 5 physical objects selected from prior work in mechanical search and not seen during training. We position the object inside the gripper in a random start orientation. We take 2 images, an RGB image from a Logitech web camera and a depth image from a Photoneo Foxy. Then we align the RGB image to the coordinate frame of the depth image. We segment out the background and the majority of the gripper from the images by only keeping pixels that have a world coordinate within a bounding box of the object. Next, we segment out the gripper using color segmentation. Finally, we crop and resize the images to 128 by 128. This final image is used for either the start image or the goal image for the network. Using this pipeline, we ensure that the depth images generated from reality are similar to the depth images generated in simulation, and the CNN trained in simulation evaluates these images effectively. Here is an example of one trial with the purple clamp object. We have images of the object in the random start and goal orientation that are 30 degrees apart. We run the controller and observe that it is able to orient the object to within 5 degrees during this trial. We also showed the gripper orienting the object. Here is another example of a trial with the sky blue bar clamp object. In this trial, the error is reduced to within 1 degree. We show the results of 10 trials on the 5 objects. The x-axis shows the progression of each trial. The y-axis shows the angle difference between the orientation at the specific iteration and the goal orientation. We plot one trial with the dark blue pipe connector object. We see in this trial that we reduce the angle error from 30 degrees to 4 degrees. Next, we plot all 10 trials with the pipe connector. Next, we plot 10 more trials with the purple clamp. Finally, we plot all 50 trials with the 5 objects. We see that for the majority of trials, the final angle error is under 10 degrees. The median final angle error is 4.2 degrees, which is higher than the median angle error of 1.5 degrees in simulation. In summary, we defined a CNN for estimating the rotation difference between 2 images, and created a controller for orienting objects using only depth images. Additionally, we showed results of experiments in simulation and reality, suggesting that the method can orient novel objects with a rotational difference of up to 30 degrees. In future work, we will address the limitation of only applying to rotations of up to 30 degrees. We also want to improve the gripper segmentation to reduce the median final angle error in physical experiments. In this trial, we cannot completely remove the gripper, and this impacts the sim-to-real transfer. 3 out of 50 trials had failure cases where the angle error increased to above 30 degrees. This is caused by self-occlusion and gripper occlusion. We hope to remove these cases. Additionally, evaluating performance of the controller in reality for symmetric objects requires more work. In this trial with the black tube object, we see that the orientation gets closer to the goal image, but due to symmetries, the angle error is misleadingly reported as increasing. I hope you enjoyed this presentation. Please check out our website and paper. If you have any questions or comments, please contact us. We also welcome ideas for collaborations. Thank you.